imagine you have a photon, a single quantum of light with some wavelength. The wavelength is proportional to the inverse of the energy. What's the energy of the photon? If you don't know the answer, then you're right. The question doesn't have an answer. The energy of the photon depends on how you observe it. Suppose you observe the photon at, say, color green. An observer moving towards it will see the color shifted to the blue, so at a higher energy, and an observer moving away from it will see it shifted to the red, so at lower energy. What's the real energy of the photon? There's no answer to that. All these energies are equally real. The energy can be arbitrarily high and the wavelength arbitrarily small, or the energy can be arbitrarily low and the wavelength arbitrarily large. The reason this happens is that in Einstein's theory, the motion of the observer changes what it means for something to be large or small, or to have a high or low energy.
Okay. So, in essence, what Sabine is saying is, photons, a quantum of light and its wavelength are proportional. So you see the wavelength of a photon is proportional to the inverse of its energy. And then when she explains that, she raises the question, well then what's the energy of the photon, right? And she goes on to say that this question does not have an answer. Like, there's no specific energy of a photon. And she says this because the energy of a photon depends on how you observe it. And what she means by that is, since the energy of a photon is inversely related to the wavelength of a photon, and since the wavelength of a photon the wavelength you observe of the photon depends on your motion. If you're moving towards it or away from it, you'll see a different color. And seeing as multiple observers can observe the same photon as different with different wavelengths, that means the energy isn't like a constant. It's different each time you observe it. And so, yes, you can argue that since you can get multiple solutions for the energy of this photon, there's not really a true energy. The energy is relative to the observer, in which that is true. I mean, depending on if you're moving towards it or away from it, the energy you will observe will be different than the energy somebody else moving in a different way will observe. But that doesn't mean the energy of the photon itself doesn't exist, or there's not an answer for it. I mean, it does, right? So what I mean is, if you take a photon and you have 3 potential observers, one sitting still, regardless of where it's at, if this is in a gravity-free space that is not expanding, it doesn't matter if it's this close to it or sitting over here or sitting over here, the wavelength will be the same if you're sitting still. And so let's say the wavelength for the sitting still observer is 500 whatever units. For an observer moving away from it, the wavelength would increase. Therefore, the energy would decrease from their perspective, from the observer moving away from it. But that doesn't, necessarily mean that the energy of the photon itself has changed. That just means the energy that the photon is exerting onto that observer has changed. So it's really just about how you say it or how you're looking at it. But I would say that, I believe that the statement, the energy of a photon depends on, the energy of a photon doesn't have an actual answer. That's just incorrect. I don't think that's true. Of course, what you observe is relative to you, right? But doesn't mean that this photon doesn't actually have energy. I don't know. Not that that's it's not too crazy to think about, but I think it's important to just be aware of that falsehood. Yeah. To give an analogy of why this is the case and why, like, the energy of the photon does exist. So imagine you are getting hit with a baseball that's traveling 100 miles an hour, and you are sitting still. The force of that, you're gonna get hit, and you're gonna feel it, right? So there's a force behind that, and I'm not calculating, but there's a force of getting hit by a 100-mile-per-hour moving baseball while you're sitting still. And if you're moving towards that baseball, say a 100-mile-per-hour baseball, and you're moving towards it at 10 miles per hour, it's like as if you're getting hit by a baseball moving at 110 miles per hour if you're sitting still. So that force is larger because your momentum and the baseball's momentum, since they're working together, you're coming towards each other, they add to each other, and so you feel a stronger force hit you. And if you're moving away from that baseball that was moving 100 miles an hour at 10 miles an hour, since you're moving away from it, your speed is going to subtract from, or your momentum is going to subtract from the momentum of the baseball. And so you'll feel it as if the ball hit you at 90 miles per hour if you were sitting still. That goes the same for this photon. I mean, like, that's saying that the energy of the photon doesn't exist is like saying the speed of that baseball doesn't exist. It's like, because if you get hit going a different speed or standing still or moving towards it, it'll feel different. Like, yeah, no fucking shit, it's gonna feel different. Like, you're moving away from it compared to you running towards it. Like, yeah, obviously it'll fucking feel different. Excuse my profanity. Like, it's not so clear when it comes to light and observing it and whatnot, but yeah, I mean, when you think about it like that, I think it's pretty clear that photons have energy. But in all fairness, Sabine Hossenfelder is a physicist of many years, and I'm a high school graduate, so yeah. But that's just how I see things. If you agree or disagree, let me know. Bye!